Hello everyone, I'm Harshavardhan Bhupathi. So I'm here to deliver the final presentation of deep learning project. And the first part I've taken the Indian diabetic retinopathy image dataset. So this is the first Indian population representative database. It's called known as IDRID, and it's the first dataset with pixel level annotations of both typical diabetic retinopathy lesions and normal retinal structures. So it has a lot of retinopathy images in it, and the URL is here. You can see that IEEE URL here, and the license is a Creative Commons attribution. So let's discuss about the structure of the dataset. So the diabetic retinopathy segmentation and grad challenge was held in the conjunction in 2018 IEEE International Symposium on Biomedical Imaging in Washington DC. So, and this dataset was made accessible to the part of event. So there are three sections that make up the dataset. The first one is segmentation. It is made up of from original fundus photos in color. That is 81 images that is divided into train and test JPG files. So next, the real world photos of lesions that has given microaneurysms and hemorrhages and hard exudates and soft exudates divided into train and test files. So coming to the disease grading, this entails like original color fundus photos and the diabetic retinopathy and diabetic macular edema ground tooth levels for severity grade. Localization. So these JPG files consist of 516 original color fundus photos and the ground truth labels indicating the location of optic disc center and the ground truth labels for location of fovea center. So you can see the sample scaled down images right here. This shows the retinopathy images that can be able to predict the diabetics here. And coming to the part two, so these all about the CIFAR10 dataset. So first, there are steps about uploading the CIFAR dataset from the local file system to the GCP. So you can see that we download all the 7 files of CIFAR dataset here. You can see in the on the screen here, and the step two is all about switching on the VM of our GCP, and step three, start SSH session, open browser window, and step 4 is you need to create JPT or JPT NTBK folder in the remote VM, and you could see the black screen here that we created the JPT NTBK folder, and we also named as a subfolder CIFAR10 data, and we upload all the files from local file system to that folder in the GCP. So you could see here this all the data. I have tried using the command lsl. You could see all the files here, and so you could see this in the Jupyter as well and on GCP. And sorry, coming to the part three. So the main step is here. So we need to build, train, and test the CNN on this CIFAR10 dataset. So basically, our let's discuss the design of CNN model. Our CNN model consists of three convolution layers and three ReLU layers. So three pooling layers and two fully connected layers. So the one for is for the finally fully connected layers. The steps involves our input data is so after the input data that has 32 by 32 by 3 pixels and it's not even required to reshape, and we have the first convolution layer has been created with the filter size of 553 comma 32, where 5 represents the filter size matrix, and 3 represents the input and 32 represent the output channels. So similarly we have built the pooling layer 1, and again we also built the second convolution layer that has that taken the filter shape of 5532 64, whereas 32 represents input channels and 64 represents output channels. And similarly the third convolution layer has also been built with the 64 input channels and 128 output channels. So after the three convolution layers are built, and we need to reshape in the data that is making it ready to the first FC layer, which is a fully connected layer. The first fully connected layer has output of 2020, sorry, 2048, and we also built a layer for it, and we need to drop out some of the input to make it easy for output, so with the final FC layer with the output size of 10, these 10 represents the 10 classes that we have in the dataset, and we need to define the loss function, and we need to calculate the softmax cross entropy loss, and we need to compute the mean of losses, and we need to create an ADAM optimizer that helps to optimize the CNN model and also set the learning rate. And we set up this 5,000 steps to train the model and test the network after every 100 steps of the training. And we need to use a run tf dot session to train and test the deep learning model, because we are using the traditional TensorFlow method instead of using the APIs, TensorFlow APIs like Keras. So So let's go back to the code and see this part 3. There you go. So we have, so some of these steps are already given by the professor. You can see the CIFAR data that has been set as being the path, and we have loaded the data here. And in coming to the next, you can see the reshape has been done on here on the data, and you can see the images how that has been displayed. And coming to the next, we need some supporting functions to re-engine the data, like encoding the labels into one-hot format and the setting of the image data to make it ready for the first convolution layer. You can see these functions here. And coming to the supporting functions, these are key functions that are required to build, train, and test the CNN model. So firstly, we need to initialize the weights in the filter. So we use the one function for that, and we need to initialize the bias and set up the convolution layer and perform convolution computation. And we also need to set up the ReLU layer, then perform the computation, and set up the pooling layer and reduce the spatial size. And for fully connected layer, you also need a function here. So coming to the phase one of building the convolution neural network, we need to import the TensorFlow as TF, you know that, and we use the placeholders here for storing the data for the inputs and labels. And for the inputs, we have the X and Y2 represents the labels, and we don't need to reshape the data since are already ready for the use. And we have created the first convolution layer, with the filter shape of 553, 32 that I have already explained in the previous description of our design in the model. And again, the convolution layer and the pooling layer, you can see the convolution layer 2 with a filter shape of 55, 32, 64, and again the ReLU layer for this convolution layer. And the pooling layer 2 has also been given here, has been defined here. And the convolution layer 3 output, which represents the third convolution layer, and ReLU layer for that. And the pooling layer that takes the output of the convolution layer 3 as input. And finally, the time comes we need to flatten the data, that is making ready the first FC layer, and we have done that here. And we have built the first FC layer, ReLU layer, and output data to dropout layer. I already told you that dropout layer, some dropouts from the fractions of the outputs randomly. And the final FC layer that represents here, he could see. And finally, we define the loss function, calculate the losses, the mean of losses, and the ADAM optimizer for optimizing the CNN model. And coming as phase two, so we need to train and test the model here. Firstly, I have to initialize the variable for initialize all the variables. And the steps have been taken is 5,000 here that I have already given or instructor by the professor. And so I have taken here for a loop for you need you need to train like 5,000 steps, and for every 100 steps I need to post the results of the testing accuracy. You could see here, so it started from point 1 to, whereas after 5,000 steps, just a second, out of 5,000 steps, it has ended up to give an accuracy of 0.6713, that is 67%. So you can see the final accuracy, testing accuracy of the first model we have built on the CIFAR dataset is around 67%. Okay, let's get back to the part 4. I have already shown you the results in the code. And let's see the part 4. So the part 4 is basically you need to compare the CNN performances of two different models on two different data sets. You can see the first CNN on CIFAR 10 data. You can see the accuracy that started from 0.12, where it ended on 6.67. Whereas you could see the MNIST data set, it has started from point 0.1, whereas it is led up to the 0.98. It's around 0.9877 accuracy, which is pretty high when compared to the model accuracy that worked on the C14 dataset. So comparing these both datasets, I could see there is a significant gap in the accuracies. So I could see that it is evident that CNN works based on the MNST data due to maybe the data sufficient sustainability. And it also depends upon the depth of the model design, like the convolution fc layers. So I believe that better results can be achieved by increasing the number of hidden layers of CNN. And the steps or epochs required during the training could also make the big difference, since If it's not optimal, that could lead to underfitting or overfitting. Since we built a simple CNN for these projects, it might not be that effective on CIFAR 10 data as it is effective on the MNHT data. So coming to the part 5. So basically the part 5 is to improve the CNN performance, the design of CNN2, and so our CNN model build consists of two layers. So, and the two layers and the two relu layers and the two pooling layers for that and two fully connected layers. So basically the model built by simply altering the first model built by the removal of convolution layer in the architecture. The steps involves below. Firstly, our input data is not required to reshape since it is good enough to deal with. It has a shape of none 32 32 comma 3. The none represents, like, it could be any scalar value in that. So whereas 32 by 32 represents the pixel size images with the three channels red, green, blue. So we create the first convolution layer, ReLU layer, and perform the computation here. The reshape image input is passed to the convolution layer with the filter size of 553, 32. So which represents a 5 by 5 filter size matrix and three inputs and 32 output channels. So the ReLU layer is built to perform computation and return outputs. The pooling layer one is built and outputs of ReLU layers is passed as input to the pooling layer. So it helps to reduce the spatial size. So it's time to create a second convolution layer and pass the outputs of pooling layer as input to it with the filter shape of 5 comma 32 comma 64, where 32 represents the input channels and 64 represents the output channels. So ReLU build performs computation on and return the outputs to the next layer as inputs. The second pooling layer has been built to take the outputs of second ReLU layer, reshaping or flattening the data, make it to be ready to the first fully connected layer. So create the first fully connected layer that takes the flattened data with output size of 4096 here and build real layer for it. So you also need to create the dropout layer and to drop out the fraction of outputs in random. So create the final FC layer with output size of 10 and compute and file produce the final outputs. So similarly, what you have done in the part 3, we need to define the loss function and calculate the softmax cross entropy and compute the mean of losses. And finally, an alarm optimizer that plays a key role in optimizing the CNN model and set the learning rate. So we also need to set up the steps. Like similarly, I've also taken the 5,000 steps in this model as well, and I also need to test the network after every 100 steps of try. And the run tf dot session is essential to test or to train and test the deep learning model. So before we go into the results, we just need to see the code that have been in the part 5. So let's go to the part 5. Similarly, you could see all the code is similar in the almost everything here, just like in the part 3. And you could see the data uploading, and since supporting functions that used to build and train the test model, just like the initializing weights, initialize bias, create convolution layers, create fully connected layers, and the placeholders for both input and labels. And so here you don't need to reshape the input placeholder because there is no point to reshape since it is ready for the use. So we create the first convolution layer, pooling layer, and second convolution layer, and ReLU layer, and the pooling layer. And we are not going for the third convolution layer. That's the biggest difference between the part 3 and part 5. So I would like to cut down the depth of the architecture to whether to see whether they could improve the performance of a CNN on this data or not. So let's see how that the results it get from these. So after finding the losses of it and using the optimizer for optimizing the model, and let's train and test the model here. Uh, so we run the tf dot session, and we could see that similarly just like that we could see the accuracy starts from point 1, whereas it has gone to just give me a second. It has gone to around could see it's gone to, on the five of the 5,000 steps gets completed. You could see that it's 0.698 accuracy. That is around 70% of accuracy. You could see that its accuracy has been increased for around 3% compared to the CNN one, where CNN one has around 67%, and the CNN two model built that is an upgrade of CNN one has shown around 70%. I could see there is a slight and a good improvement of the model performance here. So let's get back to our document and could see the results here. You got the 0.698 accuracy